cannot be represented by B spline, but can be represented by NURBS. For example, a simple curve like a circle. You cannot use B spline to generate a circle, but you can use NURBS to generate a perfect circle. Okay, so this is it. So the curves that can be represented by B spline is a subset, a smaller subset of NURBS. And originally, NURBS, which was developed in 1950s, and originally NURBS was used to design the shape of a large vehicle like a vehicle, airplane, and ships, like this. Okay. But later on, the most application of NURBS is in the field of computer science. Okay. And they can be used to represent much more different curves. So, like a machining test or surface can also be represented easily by NURBS. Okay. So let us look at this from one step by step. Let us look at how we can get the so-called NURBS from the B spline. The simplest way is that, as we say here, the NURBS has the property that each control point has different weightings. So let us look at this. So originally we had a B spline. Like the simplest way is the Bezier curve. Bezier curve. You have only one knot stem. This is 0, this is 1. Only one knot stem. So this will be a Bezier curve. As we said previously, when D equal to N, when in the B spline, when this D equal to N, then we have the so-called this should be N, this should be N, D equal to N, D equal to N. There is no P here. This should be N, N. So when D equal to N, this spline is basically a Bezier curve, simple Bezier curve. So for Bezier curve, it should be like this. The coefficient of P1 here is 1 minus U squared. For P2 it should be like this. For P3 it should be like this. That's for Bezier curve. But we can add the weighting at the control point. For example, here we add a weight. PW is what we call WI here. WI is the weighting. PW is the symbol used in the Siemens controller. They use PW as a weighting. It represents the so-called point weight. Each point you can have different weighting. Okay. So this example, we modify the original Bezier curve by adding a weighting, at the second control point. Okay, so we use PW. Okay, and in the example in the Siemens controllers. That example, the PW is the weighting can be set from 0 to 3 in a state of very small state, 10 to the minus 4. Okay. And so here we show you two different weighting. The solid line represents the original Bezier curve. Okay, and this delta with the weighting greater than 1 and larger than 1. So this solid line represents weighting equal to 1. PW is 1. When PW is 1, it's the original Bezier curve. And this one represents the weighting is larger than 1. This one represents the weighting is smaller than 1. So you can think of this. If we put more weight here, it will attract the curve to approach this point. If we put smaller weight here, it will make the curve far away from this point. So this is the weighting we put at the second point, second control point here. So similarly, if you have put a weighting here, if the weighting is larger, then the curve will be more closer to this point. Similarly for this one, you can have a different weighting. So, as you can see here, once you introduce the weighting here, you can represent much more curves than the original B-spline or Bezier curve here. Okay? This is one of the key points of the NURBS. You have a weighting. You have weighting. Okay? And because of the weighting, you have the so-called rational polynomial basis function. We will see this later. And then you can also have a non-uniformity, not equally spaced, not points, knots. Okay? Any questions so far? So this should be a simple idea. You can imagine intuitively that you can put weighting on a control point to make the original curve to have a different variations. Okay. Okay. So this is an example of the B-spline and the curve and the NURBS. Okay. So this one is the original one without weighting, and this dashed is the one with weighting. So this is the always called 1. That means the original B-spline curve, and this one is different weighting. Okay. So this is the example in the CNC controller when you type the so-called G code here. They use the so-called B-spline. The command is B-spline, simply B-spline. Okay, and you have a different weighting, then it will be different from the original B-spline. Okay, so let us look at the details. The detailed definition of the so-called NURBS. Okay. And let us look at this. We have seen this previously, that a B-spline curve of degree D can be represented in this way. Okay. Remember, this basis function, their summation must be equal to 1, right? So this will be equal to this. Because the summation of this is 1. So we just divide it by 1. So it's the same as this. Right? This is just 1. And for NURBS, we can put weighting here. Weighting here. When you have a weighting, the summation may not be equal to 1 anymore, right? So this is the original B spline, right? And we have this, right? And now, if you put weight, here, and in this case, the summation with the weighting, the summation will not be equal to 1 because of the weighting, right? You can imagine this. This is quite easy to understand, right? You put different numbers or different i's. The summation may not be equal to 1 anymore. In general, it's not equal to 1. Right? So, it's not. So in this case, it's not equal to 1. It's not good to generate a so-called curve. So we still want the coefficient of different control point. The summation of the coefficient of different control point should be equal to 1. Or we want the summation of the coefficient here should be equal to 1. So the easy way to do this is to divide it by the summation. So that means we can change this to divided by the summation. Maybe it's better to use different. We use Z. Okay. So then this coefficient in other words, originally the coefficient is this. We divided each coefficient by the summation. So in this case, the overall summation of this coefficient will be equal to 1. Right? Right? It's a straightforward way to do this. Can we see this? Okay. So the example is, for example, suppose you have 3 control points. So you may have the so-called A1, P1 plus A2, P2 plus A3, P3. If A1 plus A2 plus A3 is not equal to 1, then if we want the coefficient, the summation of the coefficient to be equal to 1, the simple way is divided by the summation. So change the coefficient to be like this: P1 plus A2 summation of this P2 A3, the same summation, right? So change the coefficient by the summation, by the summation, by the summation. this integer. So in this case, this plus this will be equal to 1. So this is the way we do it here. Right? Okay? Any question? So it's better to change the index here by saying this I is different from this I. Okay. So it's better to change this by saying okay. So we change once you have a weighting, you have to divide it by the summation of the coefficient here. So the overall coefficient of each control point will become this. Okay? And so this will be called the NURBS basis function. This is the basis function of B spline. Because you introduce weight, so the summation is not equal to 1. In order to make it equal to 1, so we divide it by this. For each coefficient, we divide it by this. So this will become rational polynomial. And this is what we call the so-called basis function for NURBS. Okay. Any questions? So each control point can have different weights. So again, when the parameter is at this end, it will be P0, and at the other end will be Pn. So it's from P0 to Pn. In between, it will not pass through. In general, it will not pass through the control point, except the endpoints. So let us look at the properties of NURBS. First of all, let us look at the so-called non-uniformity. Remember from the B spline, we have the so-called NURBS vector, NURBS. And the definition of NURBS for NURBS and B spline are the same. They have the same definition. The NURBS, in other words, the NURBS vector actually divides the parameter space into several what we call NURBS spans. Okay. And each NURBS span determines which control point will be what we call active or inactive. Okay. Maybe let me go back to okay. Sorry. Let's go back to B spline. Where is it? Okay, this example. The NURBS vector is here. We have 3 NURBS spans. Okay, they are equally spaced. 0 to 1/3, 1/3, 2/3, 2/3, and 1. So we have the whole parameter from 0 to 1. In other words, this is what we call U. The parameter space. We divide it by into 3 parts. So we have what we call three mass spans. This spans, this, and this. Okay. So when you move the parameter from 0 to 1, it will go through 3 mass spans. Each mass span, you can think of each mass span, you have control points which are active. The others are inactive. So when you move from one mass span to another mass span, some control point will become inactive. Some others will become active. And so on. Okay? And so on. So if we look at this example, from here you can see, from here within this parameter range, from 0 to 1/3, P0 will be active. P1 will be also active. And P2 also. P3 also. So 0, 1, 2, 3 will be active in this in this mass span. And P4 and P5 will not, will be inactive. When you move from this mass span to this mass span, P0 will be active. And 1, 2, 3, 4 will be active. Finally, when you move from this mass span to the next mass, the final mass span, the last 4, these 4 will be active. These 2 will be inactive. Okay? So the idea is something like this. So this is what we say. It will divide the parameter space into several mass spans, determining which control points are active and determine which their effects will be active. So whenever the parameter enters a new mass span, the new control point becomes active, and all one will become inactive. Okay? So it's what I have just explained to you for that, using that examples. You should be able to see the difference. Okay? And the length of mass span in NURBS can be different. Previously, for this spline, usually the length of each mass span is the same, equally spaced, so the same. Here, they can be different. This difference, we call it non-uniformity. So it's non-uniformity. Okay. And again, this kind of property allows NURBS to represent more curves than this one. Any questions? So when you define a NURBS curve, you choose a parameter u. You can choose it arbitrarily, without any specific reason. But sometimes it is also possible to choose some parameter u to have what we call physical meaning. So if some parameters may have physical meaning. In this case, the choice of last span can involve physical consideration. Okay. When you do not have any physical meaning, the simplest way is to use equally spaced last span. But when you have a physical meaning, you can choose it by thinking about the physical meaning of different range. For example, a simple example is that if the parameter is just time, u equal to t. U is just time. In this case, for example, for time, maybe the time from 0 to 1. This is acceleration region. This is the deceleration region. In between, you have a constant speed. Okay. In this case, you can think of the parameter range to be maybe you don't need this large as acceleration. You want to have a short acceleration region. So this one could be smaller. And similar, this one can be smaller. And the constant speed can be larger. So you can think of like a physical meaning like this, depending on your physical system. Okay. For example, you have a Feedrate system. And if you have a smaller mass, then you can have a very fast acceleration. If you have a larger inertia, then the acceleration region could be larger. Something like this. So, if your parameter has some, if your parameters have physical meaning, your choice of last span can consider the effect of physical situation. Yeah. Any question? So here I said if the parameter is time, for example, the last span will affect the acceleration deceleration of the curve. So the dynamics can be taken into account. Any question? So this is an example of the so-called non-uniformity. Okay. So here, this should be grid from bottom to up. Okay. We should look at bottom first. The last span is like this. So it's from 0 to 2.5. Okay. So you have 0 to 1, 1 to 2, and 2 to 2.5. So you have 3 last span. 0, 1, 1, 2, 2 to 2.5. Okay. And this is the basic function of degree 1. So it's degree 1, so the polynomial is degree 1. So it's linear. So it's like this, or this, like this, or this. Okay. So this is 1, 1, 1, and 2, 1. And suppose you have a weighting. So that this is okay. So you have another weighting like this. So a combination of this will become basic function of degree 2. So it will be like this. So this is as you can see, this is different from this. So it's not symmetry. It's not symmetry. Okay. And that is non-uniformity. And so non-uniform rational B-spline. So there are two key words. One is non-uniformity, another is rationality. Here. So we take a look at rationality, NURBS. So again, the definition of control point are the same for B-spline and NURBS. They have the same definition on the control points. Okay. Basically, these control points are used to determine the basic shape of the curve we want to represent. And of course, more control points can represent more complicated case, but it will accompany with more complicated manipulation, computation, and so on. Okay. In order to better describe the desired pace without increasing the complexity, NURBS introduce the weight on each control point. Okay. Similarly, like here, if you do not have a weight, if you do not introduce weight, if you want to represent, so if you use only 3 control points, you can represent this solid line only. If you want to represent, for example, this dashed line, this line, maybe you need much more control point. You need some control point in between, so that the B-spline curve can represent this dashed line. And similarly for this one, you may have much more, your control point should be much more. Okay. Okay. But here, NURBS. So, more control point can represent more complicated case. But if you have a more control point, the computation will be much more complicated, right? So NURBS introduce ways that will simplify the overall analysis and computation. But at the same time, you can represent much more different curves. So introducing weights is a good idea to make the representation of a curve simpler. Okay. However, because of the weights, the sum of the coefficient functions of each control point is not 1. So to make the sum be 1, the basis function need to be divided by the weight, the weighted sum. Okay. So this calls the so-called rational polynomial coefficient, as I have explained previously here. So this is to represent what I have explained here. So this is the reason we have the so-called rationality, rational polynomial. Why we have rational polynomial? Because we introduce weights. Why do we want to introduce weight? Because introducing weights can make can allow us to represent much more complicated curves without increasing the number of control points. We still can use a few control points, but introducing weights, we can represent much more complicated curves. This is the idea. But because of this, your coefficient will become rational polynomial. These are the reasoning. Any question? Okay. So the advantage of NURBS. Actually, this is similar to B-spline. The translation or rotation of NURBS curves can be achieved by translation or rotation of control points. Okay. In other words, if you want to represent, for example, a curve like this, if you want to represent similar curve but rotated by, for example, 30 degrees, it will become like this, 30 degrees. Then, exactly the same curve can be obtained by rotating these three control points. Or you can think of this by rotating the check polygon with the same angles. Then you can achieve the same curves. Okay. And NURBS can be used to describe analytical curve, like a circle, like a ellipse, or parabolic, or hyperbolic curve. Okay. These are the so-called conic curves. 圆锥曲线. Okay. And it can be used to describe this free-form curves, and the arbitrary smooth curve. And as you can see, there are many flexibility in constructing a NURBS curve. Okay. And compared to other interpolation methods, NURBS allow less amount of data storage. Okay. Why is this? Let us use this as example. And long time ago, once upon a time, maybe 60 years ago or 50 years ago, when people want to generate a curve like this, the only way is the small line segment, the so-called G01, the small line segment, linear line segment, to represent such curve. Using line segment to represent curve. Long time ago. In other words, the overall curve is represented by data point. You sample this curve by a set of data points, and so in computer, the curve is represented by line segment connecting this data point. At that time, this is the only way we can represent a curve. So, in this way, you need to store what? You need to store this data point. If you want to store this curve, you need to store those data points, right? And at that time, the storage is very important for the computer. But so at that time, you cannot represent too much complicated curve. Okay. And today, of course, you can store much more. For example, if you want to represent the shape of a ship like this, and if you use the line segment to represent the curve, then you need to store a lot of data points. Okay. For today's computer, that should not cause any big problem, but still cause some problem. What kind of problem? The storage, the memory requirement is huge. Okay. And a especially today we try to reduce the energy to have a so-called zero carbon emission by 2050. We don't want to spend too much